The universe is older than we can truly imagine. Light from the earliest stars has been traveling toward us for billions of years, crossing distances so vast that our minds struggle to hold them. We look up at the night sky and see not what is, but what was. The photons entering our eyes tonight left distant suns when Earth was young, when the continents had different shapes, when life itself was finding its first fragile foothold in ancient oceans. This is the nature of cosmic distance. It imposes a kind of loneliness on us, a separation enforced not by empty space alone but by time itself. We have always been travelers. Our ancestors crossed oceans in wooden ships, navigated by stars they could not reach. We built machines that carried us faster and farther, breaking barriers we once thought absolute. We learned to fly, then to escape Earth's gravity entirely, then to walk on another world. Each achievement seemed impossible until it wasn't. But there is one barrier that has never yielded, one limit that appears woven into the deepest fabric of reality. Light moves at a finite speed, and according to everything we understand about physics, nothing can move faster. This limit shapes the universe we can explore. It defines which stars we might someday visit, and which will remain forever beyond our reach. 300,000 kilometers per second. That is how fast light travels through empty space, a speed so great that light can circle Earth more than 7 times in a single second. Yet on cosmic scales, this seemingly infinite velocity becomes frustratingly slow. The nearest star beyond our sun lies more than 4 light years away, meaning any signal we send, any spacecraft we launch, would take at least 4 years to arrive, assuming it could somehow match the speed of light itself. The center of our galaxy sits 26,000 light-years distant. The nearest major galaxy, Andromeda, is 2.5 million light-years away. These numbers are not merely large, they represent a fundamental isolation, a cosmic speed limit that appears to wall us off from most of the universe. For generations, physicists have explained this limit using Einstein's theories of relativity. These theories describe a universe where space and time are not separate, absolute things, but rather aspects of a unified fabric called spacetime. Mass and energy curve this fabric, creating what we experience as gravity. Motion through space is actually motion through spacetime, and the faster you move through space, the slower you move through time. As an object with mass accelerates closer to light speed, strange things happen. Time dilates, slowing down for the traveler relative to those left behind. Lengths contract in the direction of motion. Mass increases, requiring ever more energy to accelerate further. At light speed itself, these effects become infinite. Time stops. Length compresses to zero. Mass becomes infinite. The energy required to accelerate any object with mass to light speed also becomes infinite, which is physics' way of saying it cannot be done. This is not merely a technological limitation, not simply a matter of building better engines or discovering new fuels. It represents something deeper, a structural property of the universe itself. Light moves at light speed precisely because photons have no mass. They exist in a strange state where time does not pass from their own perspective, where the moment of their creation and the moment of their absorption are, from their point of view, the same instant, even if billions of years separate those events as measured by observers like us. Anything with mass cannot join them in this timeless realm. We are bound to slower velocities, trapped in the flow of time, separated from distant stars by barriers of years and centuries and millennia. And yet, something interesting emerges when we examine relativity more carefully. The theory that imposes the speed limit also suggests ways around it, not by breaking the rules but by understanding them more completely. Einstein's equations describe how matter and energy influence spacetime, how they create curves and wells in the fabric of reality. But they also permit spacetime itself to move, to expand, to compress, to ripple in ways that do not require anything within that spacetime to exceed light speed. The universe itself is not bound by the speed limit that constrains objects moving through space. This subtle distinction opens a door, theoretical and distant, but real nonetheless. Consider the expansion of the universe. Observations show that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The most distant observable galaxies are receding at velocities greater than light speed. This does not violate relativity because the galaxies themselves are not moving through space faster than light. Instead, the space between us and them is expanding, carrying them along with it. The galaxies are like markers on a stretching rubber sheet. They remain relatively still with respect to their local neighborhood of space, but the sheet itself grows larger, increasing the distance between points. No object crosses the light-speed barrier. The barrier itself moves. This expansion is not theoretical speculation but observed fact, confirmed through multiple independent methods over decades of astronomical observation. The light from distant galaxies is stretched by this expansion, shifted toward redder wavelengths in proportion to how far the galaxies have traveled during the light's journey to us. The pattern is consistent across the entire observable universe, and the mathematics describing it emerged directly from Einstein's field equations when applied to the universe as a whole. The universe began in an extremely hot, dense state and has been expanding ever since. In the earliest moments, this expansion happened extraordinarily rapidly, a period known as cosmic inflation during which space itself expanded faster than light could cross it. Regions of the early universe that were once in contact, able to exchange light and energy, were suddenly separated by vast distances, isolated from each other not by motion through space, but by the rapid growth of space itself. If space can expand carrying distant galaxies away from us faster than light, a question naturally arises. Could space contract as well, bringing distant locations closer together? And if contraction is possible, could it be induced, controlled, shaped by some sufficiently advanced technology operating within the laws of physics? These questions are not idle speculation. They represent a legitimate avenue of theoretical investigation, one that has occupied serious physicists for decades. The idea is not to move a spacecraft through space faster than light, which relativity forbids, but to move space itself, carrying the spacecraft along with it. The distinction is subtle but crucial. It represents a shift in perspective from propulsion to geometry, from pushing against space to reshaping it. The human mind evolved to navigate three-dimensional space at speeds far slower than light. We have intuitions about distance and time, about cause and effect, that work perfectly well in everyday life but break down at cosmic scales and extreme velocities. When we think about traveling to another star, we naturally imagine a spacecraft accelerating, crossing the distance, then decelerating at the destination. We picture a journey through space, but relativity teaches us that space and time are more flexible, more interconnected than our intuitions suggest. What we experience as unchanging distance is actually part of a dynamic, four-dimensional structure that can bend and flex in response to mass and energy. Gravity itself is not a force pulling objects together, but rather the curvature of space-time causing objects to follow the straightest possible paths through bent geometry. If space-time can curve in response to mass, creating the phenomenon we call gravity, what other shapes might it take? What other configurations might be possible? Einstein's field equations are complex, highly nonlinear differential equations that relate the curvature of space-time to the distribution of matter and energy. Finding solutions to these equations is notoriously difficult. Many exact solutions are known, each describing a different space-time geometry. Some describe black holes, regions where space-time curves so severely that not even light can escape. Others describe gravitational waves, ripples in space-time that propagate outward from violent cosmic events like colliding black holes or neutron stars. Still others describe expanding universes, rotating universes, even universes with exotic topological properties. Among these solutions, a few describe geometries that seem to permit travel between distant points in less time than light would take to cross the ordinary space separating them. These solutions do not violate relativity because they do not require anything to move through space faster than light. Instead, they involve configurations of space-time where the geometry itself creates shortcuts, where the structure of space allows a path between 2 points that is shorter, in some meaningful sense, than the usual straight line through flat space. These are not wormholes, though that term is sometimes used loosely. They represent something different, something more subtle. They involve the local manipulation of space-time curvature to create a region where space contracts ahead of a traveler and expands behind them. Imagine standing on a long carpet. You could walk from one end to the other, step by step, covering the distance with your own motion. Or you could stand still and gather the carpet beneath you, pulling the far end closer while pushing the near end farther away. If you could do this continuously, you would move across the room without actually walking, carried along by the motion of the carpet itself. This metaphor, imperfect as all metaphors are, captures the essential idea. A spacecraft equipped with some hypothetical device might remain essentially motionless with respect to its immediate surrounding space, while that space itself moves, carrying the ship along with it. The space in front of the ship contracts, bringing the destination closer. The space behind expands, increasing the distance to the starting point. The ship rides this wave of compressed and expanded space, crossing vast distances without ever accelerating through space in the traditional sense. This idea was formalized in a particular mathematical solution to Einstein's equations published in the mid-1990s by a physicist working quietly at the University of Wales. The solution described a spacetime geometry with precisely these properties. A bubble of flat spacetime surrounded by a region where space contracted in front and expanded behind, creating a warp in the fabric of reality that could, in principle, move faster than light while keeping everything inside the bubble moving slower than light with respect to its local environment. The mathematics were rigorous. The solution satisfied Einstein's equations exactly. It did not violate relativity. It simply revealed that the equations permitted configurations more exotic than most physicists had seriously considered. The discovery generated considerable interest, not because it represented a practical technology, but because it demonstrated that faster than light travel was not fundamentally prohibited by the known laws of physics. The question shifted from whether such travel was possible in principle to whether the conditions required to create such a geometry could ever be achieved. This is where the challenges become clear and daunting. The solution required something unusual, something that does not appear to exist in ordinary matter. It required negative energy. Energy, as we normally understand it, is positive. It can take many forms: kinetic energy of motion, potential energy of position, thermal energy of heat, mass energy described by Einstein's famous equation. All of these are positive. They contribute to the curvature of space-time in ways that create attractive gravity, pulling things together. But the equations of general relativity do not strictly forbid negative energy. They simply describe how space-time curves in response to whatever energy and matter are present. If negative energy existed, it would curve space-time in the opposite way, creating repulsive gravity, pushing things apart. The warp geometry required enormous quantities of negative energy, arranged in a specific configuration around the traveling bubble. For years, this seemed like an insurmountable obstacle. Negative energy sounded like science fiction, a mathematical curiosity with no basis in physical reality. But quantum mechanics, the theory governing the behavior of particles and fields at the smallest scales, suggests that negative energy might exist under certain conditions. The vacuum of space, far from being empty, seethes with quantum activity. Virtual particles constantly pop into existence in particle-antiparticle pairs, existing for the briefest moments before annihilating each other. These quantum fluctuations are not mere theoretical constructs. They have measurable effects. They contribute to the properties of elementary particles. They create forces between objects at very short distances. One such effect is known as the Casimir effect, predicted in the late 1940s and measured experimentally decades later. When two uncharged metal plates are placed very close together in a vacuum, quantum fluctuations between the plates are restricted compared to the fluctuations outside. The wavelengths of virtual photons that can exist between the plates are limited by the narrow gap, while all wavelengths can exist in the open space beyond. This creates an imbalance in the quantum vacuum energy, a negative energy density between the plates compared to the surrounding vacuum. The result is a tiny attractive force pushing the plates together, a force with no classical explanation, arising purely from the quantum properties of empty space. The Casimir effect demonstrates that negative energy is not merely a mathematical possibility but a physical reality, at least on small scales. The energy density between the plates is genuinely negative compared to the vacuum energy far from the plates. This discovery gave physicists hope that perhaps, in principle, negative energy could be generated and controlled, though the amounts produced in Casimir experiments are extraordinarily small, far too small to create macroscopic effects like curving spacetime. Scaling up from the microscopic forces measured in laboratories to the cosmic scale energies required for a warp geometry represents a gap so vast that it defies current comprehension. Subsequent work on the warp geometry solution revealed additional challenges. The original configuration required an amount of negative energy equivalent to the mass of a large planet or even a star, distributed in a thin shell around the warp bubble. Later refinements reduced this requirement somewhat by optimizing the geometry, but even the most efficient designs still demanded negative energy densities and total quantities far beyond anything achievable with known physics. Moreover, creating the geometry in the first place posed problems. The equations described a static solution, a spacetime geometry that satisfied Einstein's equations, but they did not explain how such a geometry could be created from ordinary flat space. Building a warp bubble might require manipulating spacetime in ways that themselves involve faster than light motion or infinite energy, defeating the purpose. Another concern emerged around the stability of the geometry. Small perturbations, interactions with the quantum vacuum, or the presence of ordinary matter might destabilize the warp bubble, causing it to collapse or radiate away the carefully arranged negative energy. Some analysis suggested that radiation from quantum vacuum fluctuations might build up inside the bubble during travel, creating a catastrophic burst of energy when the bubble was deactivated, effectively turning the spacecraft into a bomb aimed at its destination. These problems are not deal breakers in the sense of proving faster than light travel impossible, but they highlight the enormous gap between theoretical possibility and practical implementation. Still, the fact that such solutions exist at all within the framework of general relativity is significant. It means the universe does not categorically forbid faster than light travel in every conceivable sense. It means the question is not whether it is possible, but under what conditions it might be possible, and whether those conditions can be achieved. This shifts the discussion from philosophy to engineering, albeit engineering of a kind that remains far beyond current capabilities. It invites us to think more carefully about the nature of spacetime, about the resources available in the quantum vacuum, about the ways geometry and energy interact. Around the same time that these warp geometry solutions were being explored, other physicists were investigating different ways spacetime might permit faster than light travel. Wormholes, also known as Einstein-Rosen bridges, are solutions to Einstein's equations that connect two distant regions of spacetime through a shortcut. Imagine space as a two-dimensional sheet. 2 points on the sheet might be far apart if you travel along the surface, but if you could fold the sheet and punch a hole through it, you could connect the points with a much shorter tunnel. This is the basic idea of a wormhole, a tunnel through higher dimensional spacetime that connects distant locations. Wormholes are not new. They were first described mathematically in the early 20th century as a curious feature of black hole solutions. A non-rotating black hole, according to the equations, connects to a white hole, a hypothetical object that nothing can enter but from which everything must escape. The black hole and white hole are connected by a bridge through spacetime. But this original wormhole is not traversable. It forms and collapses so quickly that nothing, not even light, can pass through before it pinches off. Moreover, the white hole end of the bridge appears to exist in a different universe or a distant part of our own universe, entirely disconnected from the black hole's region. Later work showed that traversable wormholes might be possible if the throat of the wormhole, the narrow connection between the two mouths, could be held open. This requires negative energy, the same exotic matter needed for warp geometries. The negative energy creates a repulsive gravity that prevents the throat from collapsing, allowing matter and light to pass through. The amount of negative energy required depends on the size and geometry of the wormhole, but again it is substantial, likely requiring exotic physics far beyond current capabilities. If traversable wormholes could be created or found, they would offer a different approach to faster than light travel. Instead of warping space around a moving bubble, you would step into one mouth of the wormhole and emerge from the other, potentially light years away, in a time shorter than light would take to cross the intervening ordinary space. From your perspective, you would simply walk through a tunnel, experiencing no unusual effects, moving slower than light at all times. But from the perspective of someone watching from outside, you would appear to travel faster than light by taking a shortcut through space-time. Both warp geometries and traversable wormholes share common features. Both require negative energy. Both involve manipulating the structure of space-time rather than moving through it at high velocity. Both permit faster than light travel without technically violating the local speed limit of relativity. And both raise profound questions about causality, time, and the nature of physical law. If you can travel faster than light in any reference frame, even by manipulating space-time, you open the possibility of closed time-like curves, paths through space-time that loop back on themselves, allowing travel backward in time. Imagine two events, A and B, separated by a certain distance in space and time. In ordinary relativity, there is a clear notion of causality. Light from event A can reach event B if B lies within A's future light cone, the region of space-time that light from A can reach. If B lies outside A's light cone, the events are space-like separated, meaning no signal traveling at or below light speed can connect them. In such cases, the order of A and B is not absolute. Different observers moving at different velocities will disagree about whether A happened before B or vice versa, but they will all agree that A and B are causally disconnected, that one did not and could not influence the other. Faster than light travel breaks this structure. If you can send a signal from A to B faster than light, you can connect events that would otherwise be space-like separated. And if you can do this in multiple reference frames, using warp drives or wormholes that work the same way regardless of the observer's motion, you can create situations where a signal sent faster than light in one direction, then redirected and sent faster than light in another direction, arrives back at its starting point before it left. This is the essence of a causality violation, a closed time-like curve. You could, in principle, receive a message from your future self, learn information about events that have not yet happened in your frame, and act on that information, potentially preventing those events from occurring. The possibility of time travel paradoxes has led some physicists to propose that the laws of physics must include some mechanism that prevents the creation of closed time-like curves. This idea, sometimes called the chronology protection conjecture, suggests that whenever conditions arise that would allow backward time travel, quantum effects or other physical processes intervene to prevent it. Evidence for this conjecture is limited, and it remains a topic of active debate. Some solutions to Einstein's equations that permit closed time-like curves involve exotic matter distributions or require the universe to have unusual global properties. Others involve rotating black holes or configurations of multiple wormholes. In every case, the question is whether the conditions required can actually be achieved. One approach to the causality problem involves careful analysis of what happens when you try to create a time machine using faster than light travel. Consider a single wormhole with two mouths. If the mouths are initially at rest with respect to each other, traveling through the wormhole simply transports you from one location to another without any time travel. But if one mouth is accelerated to high velocity, while the other remains stationary, time dilation effects cause time to pass differently for the two mouths. The accelerated mouth ages less than the stationary one. After some time, the two mouths, which remain connected through the wormhole's throat, are at different points in time as well as different points in space. Entering the stationary mouth and exiting the accelerated mouth could then transport you backward in time. But creating this situation requires accelerating one wormhole mouth to high velocity, which requires energy. During the acceleration, the wormhole itself becomes part of a complex space-time geometry where the usual rules about reference frames and simultaneity become entangled with the wormhole's structure. Detailed calculations suggest that as the wormhole approaches the configuration needed for backward time travel, the vacuum fluctuations of quantum fields begin to build up near the wormhole throat. These fluctuations create a back reaction, a kind of feedback effect that might destabilize the wormhole or prevent the time machine configuration from forming. The energy density of the vacuum fluctuations could become infinite at the moment the time machine would turn on, effectively preventing its creation. This is not a proof that time machines are impossible, but it is a hint that nature might have self-consistency mechanisms built into the laws of physics, ways of preventing paradoxes without requiring any explicit prohibition on faster than light travel. If these mechanisms are real and robust, they would allow warp drives and wormholes to exist for faster than light travel to distant locations, while preventing the creation of closed time-like curves that would allow backward time travel. The universe would permit you to visit distant stars quickly, but not to return and meet your younger self. Another perspective on causality and faster than light travel involves rethinking what we mean by causality itself. In everyday life, we experience time as flowing in one direction, from past to future, with causes preceding effects. This arrow of time seems fundamental, yet it emerges from statistical properties of complex systems rather than being built into the basic laws of physics at the microscopic level. Most fundamental physical laws are time-symmetric, meaning they work equally well forward or backward in time. The arrow of time arises from the second law of thermodynamics, the observation that entropy, a measure of disorder, tends to increase in closed systems. This statistical tendency gives time a direction. If we could travel backward in time and create a paradox, such as preventing our own birth, we would violate the logical consistency of events. But perhaps the universe simply does not permit inconsistent histories. Perhaps any attempt to change the past fails, not because of some enforced prohibition, but because the past that you remember already includes your time travel attempt and its consequences. This is the idea of self-consistent causal loops, where time travel is possible but paradoxes are not, because the timeline always was and always will be self-consistent. You can travel back and influence events, but you cannot change the past because your influence was always part of the past. These philosophical and physical questions remain unresolved. They represent some of the deepest puzzles in theoretical physics, touching on the nature of time, causality, and the structure of physical law. The existence of solutions to Einstein's equations that permit faster than light travel forces us to confront these questions seriously. We cannot simply dismiss them as science fiction when they emerge from the same mathematical framework that describes gravity, the expansion of the universe, and the orbit of planets with extraordinary precision. The energy requirements for warp drives and wormholes, while daunting, have inspired creative thinking about possible sources of exotic matter and negative energy. Some approaches involve trying to concentrate or amplify the Casimir effect, creating regions of space where the quantum vacuum energy is significantly negative compared to empty space far away. Others explore the properties of hypothetical particles or fields that might have negative energy densities under certain conditions. Still others consider the possibility that the quantum vacuum itself might be engineered or manipulated in ways we do not yet understand. Quantum field theory, the framework that combines quantum mechanics with special relativity, describes particles as excitations of underlying fields that permeate all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. Each field has a ground state, its lowest energy configuration, which we call the vacuum. But the vacuum is not static. It fluctuates with virtual particles appearing and disappearing constantly. These fluctuations are not just theoretical. They have been measured and confirmed in numerous experiments. They affect the energy levels of atoms, create forces between particles, and contribute to the properties of materials. The energy of the quantum vacuum is not well defined in an absolute sense. We can only measure differences in vacuum energy between different configurations. The Casimir effect measures the difference between the vacuum energy with plates present and the vacuum energy without them. What we call the zero-point energy, the energy of the vacuum where no real particles are present, might actually be enormous, but we do not notice it because we only observe changes in energy, not absolute values. This ambiguity has led to speculation that the vacuum energy might be a resource that could, in principle, be tapped or manipulated. Some proposals involve using intense electromagnetic fields to perturb the vacuum, creating regions where the properties of spacetime are altered. Others suggest that rapid acceleration or rotation might couple to the vacuum in ways that generate unusual effects. These ideas remain highly speculative, often lacking clear mathematical formulations or experimental predictions, but they represent attempts to take seriously the possibility that spacetime is not an inert background, but a dynamic, responsive medium that might be influenced by sufficiently advanced technology. One area where negative energy densities appear more naturally is in certain configurations of quantum fields in curved spacetime. When spacetime is curved, the definition of particles and vacuum states becomes observer-dependent. What one observer sees as empty vacuum, another observer in a different state of motion might see as filled with particles. This ambiguity can lead to situations where energy density, which is also observer-dependent, appears negative to certain observers. Near the event horizon of a black hole, quantum effects predict that pairs of virtual particles are constantly being created. Normally, these pairs annihilate almost immediately, but near the horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. From certain perspectives, this process involves negative energy falling into the black hole, causing it to lose mass over time through what is known as Hawking radiation. Hawking radiation is a purely quantum effect with no counterpart in classical general relativity. It shows that black holes are not entirely black but emit a faint thermal glow due to quantum processes at the horizon. The temperature of this radiation is inversely proportional to the black hole's mass, meaning small black holes are hotter and radiate more intensely than large ones. Over immense timescales, a black hole will gradually evaporate, losing mass until it disappears in a final burst of radiation. This process involves negative energy in a subtle way. The particle that falls into the black hole can be thought of as having negative energy from the perspective of an observer far from the hole, even though locally, near the horizon, all particles have positive energy. This interplay between quantum mechanics and gravity suggests that negative energy might be a generic feature of quantum fields in curved spacetime, not an exotic oddity but a natural consequence of combining the two theories. If this is the case, then understanding how to generate and control negative energy might be a matter of mastering quantum field theory in curved spacetime, a notoriously difficult area of physics, but one that might eventually yield practical insights. The challenge is that current understanding is limited to weak fields and small curvatures, far from the extreme conditions that would be needed to create warp geometries or wormholes. Another line of investigation involves reconsidering the fundamental nature of spacetime itself. General relativity treats spacetime as a smooth, continuous manifold, a geometric structure that can be described by differential equations. But at the smallest scales, near the Planck length of about 10 to the minus 30, 5 meters, quantum effects are expected to become important, and the smooth geometry of classical spacetime might break down. At these scales, spacetime might be discrete, foamy, or possess a structure entirely unlike the smooth fabric we experience at macroscopic scales. Various approaches to quantum gravity, the long-sought theory that would unify general relativity and quantum mechanics, suggest different pictures of what spacetime looks like at the Planck scale. String theory, one of the leading candidates, proposes that fundamental particles are not point-like but rather tiny vibrating strings. The different vibration modes of these strings correspond to different particles. Spacetime itself emerges from the collective behavior of strings, and its properties can change depending on the configuration. In some versions of string theory, extra dimensions of space exist, curled up at scales too small to detect directly, but influencing the forces and particles we observe. Loop quantum gravity, another approach, suggests that spacetime is quantized, made up of discrete loops and nodes rather than a continuous manifold. At macroscopic scales, these discrete elements blend together to create the appearance of smooth geometry. Much like pixels on a screen blend to create a continuous image when viewed from a distance. But at the smallest scales, the granular structure becomes important, and the familiar notions of distance and time might not apply. If space-time has a fundamental structure beyond the smooth geometry of general relativity, this structure might influence the possibilities for manipulating space-time. Perhaps configurations that seem impossible in classical general relativity become possible when quantum effects are taken into account. Or perhaps quantum gravity imposes new restrictions, preventing the creation of exotic geometries that classical theory seems to allow. Without a complete theory of quantum gravity, these questions remain open, answered only by educated guesses and speculative calculations. The search for a theory of quantum gravity has occupied some of the brightest minds in physics for decades. The difficulty lies in the fact that gravity is extraordinarily weak compared to the other forces of nature. At the scales where quantum effects are important, gravity is so feeble that it produces no measurable effects in laboratory experiments. Conversely, at the scales where gravity is strong, such as near black holes or during the Big Bang, the extreme conditions make direct observation difficult or impossible. Physicists must rely on indirect evidence, mathematical consistency, and theoretical elegance to guide their search for the right theory. One intriguing possibility that emerges from some quantum gravity theories is that spacetime might be fundamentally holographic. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume, much like a hologram encodes a three-dimensional image on a two-dimensional surface. This idea arose from studies of black hole thermodynamics and has been developed into a precise mathematical framework in certain contexts, particularly in the ADS-CFT correspondence, a duality between theories of gravity in a curved spacetime and quantum field theories without gravity in one fewer dimension. If the holographic principle is a fundamental feature of quantum gravity, it might have implications for how information is stored and processed in the universe. It suggests that spacetime is not as fundamental as we thought, but rather emerges from deeper, more abstract structures involving quantum entanglement and information. This perspective is still being explored, and its implications for faster than light travel are unclear, but it raises the possibility that manipulating spacetime might be fundamentally about manipulating information, that the geometry we experience is a kind of projection or encoding of underlying quantum data. These deep questions about the nature of spacetime connect to practical questions about faster than light travel in subtle ways. If we do not fully understand what spacetime is at the most fundamental level, we cannot be certain about what is possible or impossible in terms of manipulating it. The classical solutions to Einstein's equations that describe warp drives and wormholes are valid within the framework of general relativity, but general relativity is not the final theory. It must eventually be replaced or supplemented by a quantum theory of gravity. That new theory might reveal new possibilities or new constraints that we cannot currently anticipate. Consider the problem of singularities. General relativity predicts that under certain conditions, spacetime curvature becomes infinite, creating what are called singularities. These appear at the centers of black holes and at the beginning of the universe in the Big Bang. But infinite curvature is a sign that the theory is breaking down, that the smooth geometry of spacetime cannot be the whole story. Quantum gravity is expected to resolve these singularities, replacing the infinite curvature with some kind of quantum structure. Understanding what happens at singularities might provide insights into the limits of spacetime manipulation. The energy conditions that are violated by negative energy in warp drive and wormhole solutions might not be fundamental but rather emergent properties that hold in certain regimes, but not others. The null energy condition, for example, states that the energy density measured by any observer moving at the speed of light should be non-negative. This condition is violated by the negative energy required for warp drives and wormholes, but it is not a law of physics in the same sense as conservation of energy or charge. It is a condition that holds for classical matter fields and is often assumed in proofs of theorems in general relativity. Quantum fields, however, can violate the null energy condition under certain circumstances, as seen in the Casimir effect and Hawking radiation. There is ongoing research into quantum energy inequalities, which attempt to quantify the extent to which energy conditions can be violated in quantum field theory. These inequalities suggest that negative energy can exist, but it is limited in magnitude and extent. You cannot have arbitrarily large amounts of negative energy concentrated in an arbitrarily small region for an arbitrarily long time. The constraints are subtle and depend on the specific quantum field and space-time geometry, but they provide some bounds on what might be possible. Whether these bounds permit the creation of macroscopic warp bubbles or wormholes remains an open question, one that requires better understanding of quantum fields in curved space-time. Beyond the theoretical challenges, there are conceptual issues about what faster than light travel would mean for our understanding of the universe. If such travel were possible, and if advanced civilizations existed elsewhere in the galaxy or beyond, they might use it to explore and colonize vast regions of space. The fact that we have not observed any evidence of such civilizations, despite decades of searching, is sometimes cited as an argument against the feasibility of faster than light travel or the existence of advanced life. This is a variant of the Fermi paradox, the question of why, in a universe so vast and old, we appear to be alone. There are many possible resolutions to the Fermi paradox. Perhaps advanced civilizations are rare. Perhaps they exist but have no interest in exploration or communication. Perhaps they are here but undetected, their presence subtle or hidden. Perhaps the development of intelligence is a recent phenomenon, and we are among the first. Or perhaps faster than light travel, despite being theoretically possible, is practically unattainable, limiting even advanced civilizations to slower forms of travel or communication. Each of these possibilities has different implications for the future of humanity and our place in the cosmos. If faster than light travel is possible and eventually develop, it would transform our relationship with the universe. Stars that now seem hopelessly distant would become accessible within human lifetimes. We could explore other planetary systems, search for life, establish outposts across the galaxy. The isolation imposed by light speed limits would be broken, and the universe would become, in some sense, smaller and more connected. But this transformation would also bring challenges. How would we navigate moral and ethical questions about contact with other life forms, about the use of resources on distant worlds, about the governance of a civilization spread across light years? Even without faster than light travel, humanity has begun to think seriously about interstellar exploration. Concepts for robotic probes that could reach nearby stars within a century using conventional propulsion have been developed. These missions would require enormous energy and advanced technology, but they involve no physics beyond what we currently understand. Lasers or particle beams could accelerate lightweight probes to a significant fraction of light speed, allowing them to reach Alpha Centauri or other nearby stars within the lifetime of the people who launched them. The probes would send back data, images, and measurements, expanding our knowledge of other star systems, even if human travelers could not follow. Such missions highlight the patience required for interstellar exploration at sublight speeds. A probe launched today would not return data for decades, and any response to that data would take decades more. Conversations with colonists or explorers at another star would be slow, measured in years rather than seconds. Civilizations might rise and fall in the time it takes a message to cross the void. This pace is alien to our experience, but it is the reality imposed by the structure of spacetime as we understand it. Faster than light travel, if it exists, would change this calculus entirely. But even if it is possible in principle, the engineering challenges are staggering. Generating and controlling negative energy, manipulating spacetime curvature on macroscopic scales, ensuring stability and safety. These are problems that might take centuries or millennia to solve, if they can be solved at all. They require not just incremental improvements in technology, but fundamental breakthroughs in our understanding of physics. We would need to master quantum field theory in curved spacetime, develop a complete theory of quantum gravity, and then figure out how to apply that theory to build actual devices. This is not to say it is impossible. History is full of technologies that seemed impossible until they were achieved. Heavier than air flight, nuclear energy, semiconductor electronics, space travel, all were once considered fanciful or unattainable. The difference is that those technologies, while difficult, did not require new physics. They were applications of known principles. Faster than light travel, by contrast, sits at the very edge of theoretical possibility, relying on aspects of physics that are not yet fully understood. It is less like building the first airplane and more like building the first airplane before the laws of aerodynamics have been discovered. Yet the fact that solutions to Einstein's equations permit such geometries is significant. It means the question is not whether faster than light travel is allowed by the laws of physics as we currently understand them, but whether the conditions required can be achieved. This is a question of engineering in the broadest sense, of whether the resources and knowledge exist or can be developed to create the necessary configurations of matter, energy, and space-time. It is a question that cannot be answered definitively today, but it is a legitimate scientific question, not mere fantasy. Some researchers have explored whether there might be observable signatures of warp drive technology, assuming it exists and is being used by advanced civilizations. A spacecraft surrounded by a warp bubble would create unusual distortions in space-time, potentially producing gravitational waves or other detectable effects. If an advanced civilization were traveling through our galaxy using warp drives, their passage might leave traces that could be detected by sensitive instruments. So far, no such signatures have been found, but the search has only just begun, and we may not yet know what to look for. Gravitational wave detectors, such as LIGO and Virgo, have opened a new window on the universe, allowing us to observe ripples in spacetime caused by colliding black holes and neutron stars. These detectors are sensitive to specific frequencies and patterns of gravitational waves. A warp bubble, if it existed, might produce different patterns, perhaps at different frequencies. Future detectors with greater sensitivity or different frequency ranges might be able to detect such anomalies if they exist. This is speculative, but it illustrates how theoretical ideas about faster than light travel can lead to concrete observational strategies. Another potential signature involves the interaction of a warp bubble with the interstellar medium. As the bubble moves through space, it would interact with gas, dust, and radiation, potentially creating a bow shock or other observable phenomenon. The details depend on the specific geometry of the warp bubble and the properties of the surrounding medium, but in principle, such interactions could produce light, radio waves, or high-energy particles that could be detected from a distance. Again, no such signatures have been observed, but we have only recently begun to consider what they might look like. The absence of evidence is not evidence of absence, especially when we are searching for phenomena we barely understand. The universe is vast, and our observations cover only a tiny fraction of it. Even if warp drives are being used by advanced civilizations, we might not have looked in the right places, at the right times, or with the right instruments, or the signatures might be subtle, buried in noise, or mistaken for natural phenomena. Science progresses by ruling out possibilities and refining our understanding, and the search for signs of faster than light travel is part of that process. It is also worth considering the possibility that faster than light travel, even if possible, might not be the most efficient or desirable way to explore the universe. Virtual presence through advanced communication, uploading consciousness into durable substrates, or creating artificial intelligence that does not require life support might be more practical for interstellar exploration. An advanced civilization might send information rather than matter, reconstructing travelers at the destination using local resources, or they might extend their lifespans or slow their subjective experience of time, making even centuries-long journeys feel brief. These alternatives do not require exotic physics, only advanced technology and a different approach to what it means to explore. The human desire to travel, to see new places and experience them firsthand, might not be universal. Other forms of intelligence might value different things, might find satisfaction in ways that do not involve physical presence, or they might have transcended the limitations of biology entirely, existing as patterns of information that can be transmitted at light speed and instantiated wherever needed. In such a scenario, faster than light travel becomes unnecessary, a relic of biological constraints that no longer apply. These reflections bring us back to fundamental questions about what we want and why. Do we want to visit other stars because we hope to find life to learn about the universe, to expand humanity's reach? Or is the desire rooted in something deeper, a need to push boundaries, to overcome limits, to prove that nothing is truly impossible? Both motivations are valid, but they lead to different paths. If our goal is knowledge, we can gain much through remote observation, through telescopes and probes and signals. If our goal is presence, to plant a flag or breathe the air of another world, then we need to send ourselves, and faster. Then light travel becomes essential. The history of exploration on Earth shows that motivations are complex and often mixed. Explorers sought wealth, knowledge, adventure, escape, glory. They risked everything for reasons that were not always rational, driven by curiosity and ambition, and sometimes desperation. The same will likely be true for space exploration. Some will go to find resources, others to satisfy curiosity, others to escape problems on Earth or to build something new. The drive to explore seems intrinsic to human nature, though it manifests differently in different individuals and cultures. If we do achieve faster than light travel, it will not be because a single breakthrough suddenly makes it possible. It will be the result of centuries of incremental progress, of building knowledge and technology piece by piece, of solving problems that seem insurmountable today. It will require collaboration across generations, a sustained commitment to science and exploration, and perhaps a bit of luck. The path forward is uncertain, filled with obstacles we can see and others we cannot yet imagine. But uncertainty is not the same as impossibility. Consider how much we have learned in the past century. In the early 1900s, atoms were still theoretical. Quantum mechanics did not exist, and the structure of the universe was unknown. We did not know that other galaxies existed beyond our own. We did not know about nuclear energy, black holes, or the expansion of spacetime. We had not yet developed general relativity, quantum field theory, or the standard model of particle physics. Every major component of our current understanding of the universe was discovered or developed in the last 100 years. Extrapolating forward, it is reasonable to expect that the next century will bring equally profound discoveries. We will develop a theory of quantum gravity. We will understand dark matter and dark energy, the mysterious components that make up most of the universe's mass and energy. We will probe the earliest moments of the Big Bang and perhaps see beyond it. We will detect gravitational waves from exotic sources and observe phenomena we cannot currently imagine. Some of these discoveries may reveal new possibilities for manipulating spacetime, new sources of energy, new principles that make faster than light travel more feasible. Or they may reveal that the barriers are more fundamental than we thought, that the universe has built-in protections against causality violations, that negative energy cannot be generated in the quantities required. Either outcome would be valuable. Science progresses by learning what is true, not by confirming what we hope is true. If faster, then light travel is impossible, understanding why would deepen our knowledge of the laws of nature. If it is possible, understanding how would open the universe to exploration. In the meantime, we can appreciate the universe as it is, vast and ancient, filled with wonders that light has carried to us across unimaginable distances. We can marvel at the fact that the photons entering our eyes tonight began their journey long before humans existed, that the stars we see are not as they are now, but as they were. This temporal displacement, this looking into the past, is a consequence of light's finite speed, a feature of the universe that shapes our experience of it. The speed of light is not just a speed limit, but a fundamental constant that appears throughout physics, linking space and time, energy and mass, electricity and magnetism. It sets the scale for how fast information can propagate, how quickly cause and effect can be connected, how the universe evolves. A universe with a different speed of light would be profoundly different, with different chemistry, different stars, different possibilities for life. The value of this constant, like other fundamental constants, seems finely tuned to allow complexity and structure to emerge. Why this is so remains one of the deepest mysteries in physics. Some theories suggest that the constants of nature are not truly constant, but vary across different regions of a vast multiverse, each region with different values, different laws, different outcomes. In most regions, the constants would not permit life or complexity, and those regions would remain empty and sterile. We find ourselves in a region where the constants allow stars, planets, and life because only such regions can produce observers to ask the question. This is the anthropic principle, a controversial idea that shifts the question from why the constants have the values they do to why we observe the values we do. Whether the multiverse exists or not, the universe we inhabit has the properties it has, and we must work within those constraints. The speed of light is what it is. Spacetime has the structure it has. Energy and matter interact according to specific laws. These are the rules of the game, and our challenge is to understand them well enough to see what is possible within them. Faster than light travel, if it exists, will be found in the subtle interplay of those rules, in the loopholes and exceptions that detailed analysis reveals. The mathematics of general relativity are rich and complex, full of surprising solutions and unexpected behaviors. Physicists have spent over a century exploring them, finding black holes, gravitational waves, expanding universes, and countless other phenomena. Each discovery has deepened our understanding, but the equations still hold secrets. New solutions are found regularly, describing spacetime geometries that had not been considered before. Some are purely academic curiosities, mathematical constructs with no physical realization. Others might represent real possibilities, configurations that could exist under the right conditions. Warp drive solutions are among these. They represent a corner of the space of solutions to Einstein's equations that most physicists did not think to explore until relatively recently. Their discovery did not change the equations, which have been known for over 100 years, but it changed what we thought the equations could describe. This is a common pattern in physics. The equations are often more general, more permissive than our intuitions suggest. We limit ourselves by thinking in familiar terms, by assuming that the solutions we know are representative of all possible solutions. When someone comes along and finds something new, it expands the landscape of possibilities. This is one reason why theoretical physics is valuable even when it does not lead to immediate applications. It maps out what is possible, what is forbidden, where the boundaries lie. It provides a framework for thinking about questions that might not have practical relevance today, but could become important in the future. Faster than light travel is such a question. It may never be achieved, but exploring the theoretical possibilities teaches us about relativity, quantum mechanics, energy, and spacetime in ways that purely practical research might not. Education and public understanding of science also benefit from engaging with these ideas. Faster than light travel captures the imagination in a way that few other topics do. It connects to deeply human desires for exploration and transcendence. When people learn about warp drives or wormholes, they are motivated to learn about relativity, about how spacetime works, about the nature of energy and mass. They encounter concepts like light cones, geodesics, and curvature that are central to modern physics. Even if faster than light travel remains forever out of reach, the journey to understand it is worthwhile. Science fiction has played a role in popularizing these ideas, though not always accurately. Shows and movies depict warp drives and hyperdrives as routine technology, glossing over the enormous challenges and exotic physics involved. This can create misconceptions, leading people to think that faster than light travel is just a matter of engineering, that it will become possible as soon as we develop the right materials or energy sources. The reality is more nuanced. It is not just an engineering problem, but a fundamental question about the nature of reality. Still, science fiction serves a purpose. It inspires curiosity, encourages young people to pursue science and engineering, and explores the social and ethical implications of technologies that may or may not ever exist. It asks what-if questions that can reveal insights about ourselves and our societies. What if we could travel to other stars? What would we do? How would it change us? These are valuable questions, even if the technology remains speculative. As our understanding of physics deepens, the boundary between science fiction and science shifts. Ideas that once seemed fantastical become plausible or even reality. Black holes were once considered purely theoretical, possibly not even real. Now we have images of their event horizons and have detected their collisions through gravitational waves. Gravitational waves themselves were uncertain for decades, predicted by theory but not observed. until their direct detection in 2015 confirmed their existence beyond doubt. Each confirmation of a theoretical prediction builds confidence in the framework of relativity and encourages exploration of its more exotic implications. The detection of gravitational waves opened new possibilities for observing the universe. We are no longer limited to electromagnetic radiation, the light and radio waves and gamma rays that telescopes have collected for centuries. We can now listen to the vibrations of spacetime itself, hearing the collisions of massive objects billions of light years away. Future detectors will be more sensitive, able to observe a wider range of sources. Space-based detectors will access frequencies that ground-based instruments cannot, revealing new classes of phenomena. These observations might eventually provide indirect evidence relevant to faster than light travel. If spacetime can be manipulated in the ways required for warp drives, those manipulations might produce gravitational signatures. If traversable wormholes exist, either naturally or artificially created, they might emit gravitational waves or interact with the surrounding spacetime in detectable ways. Even if we cannot create such structures ourselves, observing them in nature or as the product of advanced civilizations would tell us that they are possible, that the theoretical solutions correspond to physical reality. Conversely, if we continue to observe the universe and never find any evidence of such exotic structures, that would also be informative. It would suggest that the conditions required are even more restrictive than we thought, or that nature has mechanisms preventing their formation. Either way, observation and theory inform each other, each guiding the other toward a deeper understanding. The interplay between theory and observation is central to how science works. Theory predicts phenomena and observation confirms or refutes those predictions. When observation reveals something unexpected, theory must adapt, expanding to accommodate the new data. This cycle has driven progress for centuries. Newton's laws gave way to Einstein's relativity when observations of Mercury's orbit and the bending of starlight could not be explained by Newtonian gravity. Quantum mechanics emerged from observations of atomic spectra and the photoelectric effect that classical physics could not account for. Each revolution was driven by the interplay of careful observation and bold theoretical insight. Today we are in a similar position with quantum gravity and the nature of space-time at the smallest scales. We have theoretical frameworks, but they make predictions that are difficult or impossible to test with current technology. The energies required to probe the Planck scale are far beyond anything we can produce in particle accelerators. The distances involved are far smaller than anything we can measure directly. We must rely on indirect evidence, on precision measurements of known phenomena, on cosmological observations that might reveal hints of quantum gravity effects in the early universe. Some approaches to quantum gravity make testable predictions. String theory, for example, predicts the existence of extra dimensions and supersymmetric particles, though these have not yet been observed. Loop quantum gravity predicts modifications to the behavior of light traveling across cosmic distances, tiny effects that might be detectable with sufficiently sensitive instruments. Other approaches suggest that spacetime itself might have a minimum length scale, below which the concept of distance breaks down, leading to observable consequences in high-energy physics or cosmology. Testing these ideas requires pushing technology to its limits and beyond. It requires international collaboration, long-term funding, and a willingness to pursue questions whose answers may not come for decades. It requires patience and persistence, qualities that are sometimes in short supply in a world that values quick results and immediate applications. But fundamental physics has always been a long-term endeavor. The insights gained today build on work done generations ago, and the work we do today will bear fruit for generations to come. This long-term perspective is essential when thinking about faster than light travel. Even if we determine that it is possible in principle, the practical realization might take centuries. We would need to develop technologies that do not yet exist, to harness energies on scales we have never achieved, to manipulate space-time in ways that require a complete understanding of quantum gravity. Each step would build on the previous one, each generation contributing a piece of the puzzle. This is how great achievements happen, through sustained effort over time, through the accumulation of knowledge and skill. there are precedents for such long-term projects. The development of nuclear energy took decades, from the discovery of radioactivity to the first controlled chain reaction to the deployment of power plants. Space exploration has spanned generations, from the first satellites to the moon landings to the current exploration of Mars and beyond. Each stage seemed impossible until it was achieved, and each achievement opened new possibilities. Faster than light travel, if it happens, will follow a similar path, beginning with theoretical work, moving through experimental validation, advancing to proof of concept demonstrations, and eventually reaching practical application. We are currently in the earliest stage, where the theoretical foundations are being laid. We have solutions to Einstein's equations that describe the geometries involved. We have some understanding of the energy requirements and the role of negative energy. We have identified the major obstacles and begun to explore possible ways around them. This is the groundwork, the necessary first step before any practical work can begin. It may seem abstract and removed from reality, but it is essential. Without a solid theoretical foundation, we cannot know what is possible or how to achieve it. As research continues, our understanding will deepen. New insights from quantum gravity might reveal that warp drives require less exotic energy than currently thought, or that the energy can be generated through processes we have not yet considered. Advances in materials science might lead to structures that can withstand the intense forces involved. Progress in computational methods might allow us to simulate warp bubble dynamics, identifying stable configurations that minimize energy requirements. Each advance brings us closer to knowing whether faster than light travel is achievable. At the same time, we must remain open to the possibility that the answer is no, that the barriers are insurmountable, that the universe does not permit faster than light travel in any practical sense. This would not be a failure of science but a success, a deepening of our understanding of natural law. Knowing the limits of what is possible is as valuable as discovering new possibilities. It shapes our expectations, guides our efforts, and helps us appreciate the universe as it is rather than as we wish it to be. Whether faster than light travel is possible or not, the journey to find out is worthwhile. It pushes the boundaries of knowledge, inspires new generations of scientists and engineers, and forces us to confront the deepest questions about the nature of reality. It reminds us that the universe is stranger and more wonderful than our everyday experience suggests, that the laws of physics permit phenomena far beyond what we encounter in daily life. Black holes, neutron stars, gravitational waves, quantum entanglement, these are all real, all part of the universe we inhabit, all predicted by theories that seemed abstract when first developed. Faster than light travel sits at the edge of this landscape, neither clearly possible nor clearly impossible, waiting for further investigation. It challenges us to think carefully, to do the math, to check our assumptions, to follow the evidence wherever it leads. It is a problem worthy of our best efforts, regardless of the outcome. And in pursuing it, we learn not just about warp drives and wormholes, but about space-time, energy, causality, and the fundamental structure of the cosmos. The universe has a way of surprising us. Time and again, phenomena we thought impossible have turned out to be real. Atoms were once considered philosophical constructs. Radioactivity, the quantum nature of light, the existence of antimatter, all were unexpected discoveries that reshaped our understanding. The expansion of the universe, predicted by Einstein's equations but initially dismissed even by Einstein himself, turned out to be one of the most fundamental features of cosmology. We cannot predict what future discoveries will reveal, but history suggests that reality is often richer and stranger than our theories anticipate. This gives reason for cautious optimism. While we should not assume that faster than light travel is possible just because we want it to be, we should also not assume it is impossible just because it seems difficult or exotic. The universe operates according to laws that we are still learning to understand. Our current theories are powerful but incomplete. They work beautifully in the regimes where we have tested them, but may break down or require modification in extreme conditions. The final theory, whatever it turns out to be, will incorporate general relativity and quantum mechanics as special cases, valid in their respective domains but subsumed into a more comprehensive framework. That final theory might permit faster than light travel, or it might forbid it through mechanisms we have not yet discovered, or it might reveal that the question itself is ill-posed, that our concepts of space, time, and travel are too limited to capture the full reality. We will not know until we get there, and the journey to that understanding is one of the great adventures of the human intellect. It requires the best minds of each generation working together, building on the insights of those who came before, pushing the boundaries of what is known. Education and public engagement are crucial to sustaining this effort. The people who will solve these problems have not yet been born. We must inspire them, train them, give them the tools and opportunities they need to continue the work. This means funding for basic research, support for universities and research institutions, programs to encourage young people to pursue science and mathematics. It means creating a culture that values curiosity, that celebrates discovery, that understands that knowledge for its own sake is a worthy goal. It also means communicating science to the broader public, helping people understand not just the results but the process, the way scientists think, the standards of evidence, the careful reasoning that separates science from speculation. Faster than light travel is an excellent topic for this because it sits at the intersection of rigorous physics and popular imagination. It gives scientists a chance to explain what is known, what is unknown, how we determine the difference, and why the questions matter. When done well, this communication builds trust in science and helps people appreciate the complexity and beauty of the universe. The challenges we face in understanding faster than light travel are not just technical but also conceptual. We must learn to think in new ways, to question assumptions that seem obvious, to entertain ideas that violate our intuitions. This is difficult because our brains evolved to navigate a world of medium-sized objects moving at slow speeds. We have strong intuitions about space, time, and causality that work well in everyday life but fail at extremes. Overcoming these intuitions requires training, practice, and a willingness to trust the mathematics even when it leads to counterintuitive conclusions. Relativity itself is full of such conclusions. Time dilation, length contraction, the relativity of simultaneity all violate our everyday intuitions but are firmly established by experiment. Quantum mechanics is even worse, with particles that exist in superpositions of states that are entangled across arbitrary distances that behave differently when observed. These phenomena are real, but they feel alien to us. We accept them because the mathematics works and the experiments confirm the predictions, but they remain strange. Faster than light travel, if it exists, will likely be similarly strange. It will involve phenomena that violate our intuitions, that require careful mathematical reasoning to understand. It may involve manipulating spacetime in ways that seem impossible, using energy sources that challenge our current understanding, navigating causality issues that our brains are not equipped to handle intuitively. Accepting this strangeness, working with it rather than against it, is part of what it means to do physics at the frontiers of knowledge. The philosophical implications of faster than light travel are profound. If we can travel backward in time, even in principle, what does that mean for free will, for the nature of the past and future, for the structure of reality? If the universe permits closed time-like curves, does that mean the future is fixed, already written, just waiting to be experienced? Or does it mean something stranger, that multiple timelines coexist, that the universe branches in ways we do not yet understand? These questions touch on deep issues in metaphysics and the philosophy of science, areas where physics, philosophy, and even theology intersect. Some physicists argue that we should take the mathematics at face value, that if the equations permit closed time-like curves, then such curves are real and we must grapple with their implications. Others argue that the equations are showing us the boundaries of their own validity, that when we encounter paradoxes or infinities, it is a sign that we need a more complete theory. Both perspectives are valuable. The first encourages us to think boldly, to explore the full landscape of possibilities. The second reminds us to remain grounded, to recognize when we are reaching the limits of our current understanding. Ultimately, the resolution of these questions will come from a combination of theoretical insight and empirical evidence. We need better theories to understand what is possible, and we need observations to test those theories. The interplay between theory and experiment is what makes science reliable, what distinguishes it from pure speculation. Theories that make no testable predictions are interesting as mathematics or philosophy, but cannot be considered science in the strictest sense. They must connect to reality, must predict phenomena that can be observed, measured, confirmed, or refuted. For faster than light travel, the path to testable predictions is not yet clear. We might look for indirect signatures, as mentioned earlier, or we might develop technologies that probe the quantum vacuum, manipulate spacetime on small scales, or test the limits of energy conditions. Each experiment, even if it does not directly test faster than light travel, contributes to our understanding of the underlying physics. Each measurement of gravitational waves, each test of quantum field theory, each probe of high-energy phenomena adds a piece to the puzzle. In the meantime, theoretical work continues. Physicists refine the warp drive solutions, exploring different geometries, optimizing energy requirements, analyzing stability. They develop new mathematical tools to handle the complexities of quantum fields in curved spacetime. They search for connections between different areas of physics, looking for unifying principles that might simplify the picture. This work is often highly technical, involving advanced mathematics and abstract concepts, but it is the foundation on which future progress will be built. There is also value in simply maintaining the question, in keeping the possibility of faster than light travel alive in the scientific imagination. Questions that are dismissed as impossible sometimes turn out to be merely difficult. Problems that seem intractable sometimes yield to new approaches, new tools, new insights. By continuing to work on the problem, even in the absence of immediate progress, we ensure that when a breakthrough comes, we are ready to recognize it and capitalize on it. History provides examples of this. Heavier than air flight was considered impossible by many serious scientists in the late 19th century. They had good reasons, based on calculations of the power required and the materials available. But they were wrong, not because the calculations were incorrect, but because they did not account for all the factors, because they lacked the insights that the Wright brothers and others eventually discovered. The breakthrough came not from a sudden revolution, but from incremental progress, from careful experimentation, from a willingness to try again after repeated failures. Nuclear energy followed a similar path. Rutherford, who discovered the atomic nucleus, famously said that anyone who expected to derive energy from atomic transformations was talking moonshine. He was one of the greatest experimental physicists of his time, and he was wrong. Within a few decades, nuclear reactors and weapons had been developed, proving that atomic energy was not only possible but enormously powerful. The key was understanding the chain reaction, a concept that was not obvious from the basic physics, but emerged from careful theoretical and experimental work. These examples show that expert opinion, while valuable, is not infallible. When experts say something is impossible, they are usually basing that judgment on current understanding, current technology, current assumptions. If any of those change, the judgment may change as well. This is not to say that we should ignore expert opinion or embrace wishful thinking. It is to say that we should distinguish between what is forbidden by well-established laws of physics and what is merely beyond current capabilities. Faster than light travel falls into the latter category. It is not forbidden by known laws, but it requires conditions that we do not know how to achieve. The distinction is important because it guides how we allocate resources and attention. If something is truly impossible, forbidden by fundamental law, there is no point spending resources trying to achieve it. But if something is merely very difficult, requiring advances in understanding and technology, then continued effort is justified, especially if the payoff would be transformative. Faster than light travel certainly qualifies as transformative. It would change everything: our relationship with the cosmos, our sense of possibility, our future as a species. This does not mean we should invest heavily in building warp drives tomorrow. It means we should continue to invest in the fundamental physics that underlies the question. We should support research in quantum gravity, in high-energy physics, in gravitational wave astronomy, in quantum field theory. We should encourage students to pursue these areas, to to ask difficult questions, to challenge conventional wisdom. We should maintain a portfolio of research that includes speculative, long-term projects alongside more practical, near-term work. This balanced approach maximizes the chances of breakthroughs while ensuring that science continues to address immediate needs. Funding agencies and institutions play a crucial role in this. They decide which projects to support, which directions to pursue, how to balance risk and reward. In recent decades, there has been pressure to focus on research with clear applications, with short timelines, with measurable outcomes. This is understandable, especially in times of limited resources, but it risks neglecting the kind of fundamental, curiosity-driven research that has historically led to the most important breakthroughs. Faster than light travel is exactly the kind of long-term, speculative question that requires sustained support without the expectation of immediate results. Private funding can also play a role. Philanthropists and visionaries who understand the value of fundamental research can support work that might not fit traditional funding models. This has happened before, with private observatories, research institutes, and grants enabling work that governments or universities could not support. The challenge is ensuring that such funding supports rigorous science rather than pseudoscience or wishful thinking. Quality control, peer review, and intellectual standards are essential to maintaining the integrity of the research. Collaboration is another key ingredient. The problems at the frontier of physics are too complex for any individual or small group to solve alone. They require expertise from multiple disciplines, from general relativity to quantum field theory to cosmology to mathematics to experimental physics. They require sharing data, ideas, and tools across institutions and borders. International collaboration has been a hallmark of modern physics, from the development of quantum mechanics in the 1920s to the detection of gravitational waves in the 2010s. Faster than light travel, if it is ever achieved, will be the result of similar collaboration spanning decades or centuries, involving thousands of contributors. The question of whether humanity should pursue faster than light travel is separate from whether it is possible. Even if it becomes technically feasible, there may be good reasons not to do it. The energy requirements might be so enormous that they strain available resources. The risks might be too high, the potential for accidents or unintended consequences too great. The ethical implications of enabling such travel might raise concerns about who has access, about the impact on other life forms or environments, about the militarization of the technology. These are legitimate concerns, deserving serious consideration, but they are not reasons to stop investigating the underlying physics. Understanding what is possible is a prerequisite to making informed decisions about what should be done. We cannot assess the risks and benefits of a technology we do not understand. The time to debate the ethics and policy is when the technology becomes feasible, not before. Until then, our focus should be on learning, on expanding the boundaries of knowledge, on following the evidence wherever it leads. There is also the question of what happens if we determine that faster than light travel is fundamentally impossible. Would that be a disappointment, a closure of possibilities, a limitation on humanity's future? Or would it be liberating, a clarification of the rules, an opportunity to focus on what is achievable? Different people will have different reactions, but for science, the answer is valuable regardless of what it is. Knowing the truth is always better than clinging to false hope. If faster than light travel is impossible, we will need to reconsider our approach to interstellar exploration. We might focus on generation ships, vast vessels that travel for centuries, carrying entire communities to distant stars. We might develop suspended animation or other technologies to extend human lifespans or reduce subjective travel time. We might send robotic probes or artificial intelligence, entities that do not require life support and can operate over timescales that would be unimaginable for biological beings. Each of these approaches has its own challenges, but they do not require new physics, only advanced engineering. Alternatively, we might shift our focus from physical exploration to virtual or informational exploration. Advanced telescopes and instruments might allow us to study distant planets in such detail that physical travel becomes unnecessary. We could search for biosignatures, technosignatures, signs of intelligence or civilization, without ever leaving our solar system. We could participate in a cosmic conversation, exchanging messages with other civilizations across light years, sharing knowledge and culture even if we never meet in person. This slower, more patient form of exploration might be more in harmony with the structure of the universe, more sustainable over the long term. These are not failures or compromises. They are different visions of what it means to explore, to expand, to reach beyond ourselves. The universe is vast enough to accommodate many approaches, many strategies, many dreams. Faster than light travel is one possibility among many, exciting and transformative, but not the only path forward. What matters is that we continue to explore, that we continue to ask questions, that we continue to push the boundaries of what we know and what we can do. The story of humanity is a story of curiosity and innovation, of overcoming obstacles and adapting to new realities. We have faced many challenges over our history, from ice ages to plagues to wars to the existential threats we now confront. Each time we have survived by learning, by working together, by finding new solutions to old problems. The challenges of interstellar exploration are different in scale but not in kind. They require the same qualities that have carried us this far: patience, ingenuity, cooperation, and a willingness to dream big while working pragmatically toward achievable goals. Looking up at the stars, we see the universe as it was, light from distant suns that has traveled for years or centuries or millennia to reach our eyes. We are observers of the past, witnesses to events that unfolded long before we existed. This temporal displacement is a fundamental feature of the cosmos, a consequence of light's finite speed and the vast distances involved. It imposes a kind of isolation, a separation not just in space but in time. The stars we see tonight may have changed or even died since their light began its journey toward us. This isolation is both humbling and inspiring. It reminds us of our smallness, our brief existence in a universe that is billions of years old and will continue for billions more. But it also inspires awe, wonder, a desire to understand and connect. We are part of this universe, made of the same elements forged in the hearts of stars, governed by the same laws, subject to the same limits. Yet we have the capacity to observe, to think, to imagine, to ask why. This capacity is precious, perhaps unique, certainly rare. If we achieve faster than light travel, we will overcome one aspect of cosmic isolation. We will be able to visit distant stars, to see them not as they were but as they are, to explore their planets, to search for life. We will connect regions of space that are currently separated by uncrossable gulfs of time. We will make the universe, in some sense, smaller and more accessible. But we will not overcome the fundamental loneliness of consciousness, the experience of being a self-aware entity in a vast and largely indifferent cosmos. That loneliness is existential, not merely spatial. It cannot be solved by technology, only by connection, by finding or creating meaning, by recognizing our place in the larger whole. Perhaps this is part of why faster than light travel captures our imagination. It represents not just a technological achievement, but a transcendence, a breaking of chains, a victory over the limits that constrain us. It is a symbol of human aspiration, of the refusal to accept that anything is truly impossible. Whether we achieve it or not, the desire itself is meaningful. It speaks to something deep in human nature, a restlessness, a need to explore, a belief that there is always more to discover. The universe does not care about our desires. It operates according to laws that exist independently of our wishes. But within those laws, there is room for agency, for creativity, for the unexpected. Evolution did not have to produce beings capable of asking questions about faster than light travel, but it did. Chemistry did not have to allow the formation of brains complex enough to understand Einstein's equations, but it does. The universe permits the existence of observers who can contemplate its structure, wonder at its vastness, and imagine ways to traverse it. This is itself a kind of miracle, though not a supernatural one. It is an emergent property of complex systems, a consequence of physics and chemistry and biology operating over billions of years. Consciousness, intelligence, the capacity for abstract thought, these are all natural phenomena, products of material processes, yet they enable experiences and achievements that seem to transcend the merely material. We are matter that has become aware of itself, that can think about its own origins and fate, that can build technologies and theories extending far beyond the immediate needs of survival. In this context, the quest to achieve faster than light travel is part of a larger story, the story of matter organizing itself into patterns of increasing complexity and capability. From the first atoms forming after the Big Bang, to the first stars and planets, to the first molecules capable of replication, to the first cells, to the first brains, to the first civilizations, the trend has been toward greater organization, greater information processing, greater ability to sense and manipulate the environment. Each step opens new possibilities, new challenges, new questions. Where this trajectory leads is unknown. We might be near the beginning of a process that will continue for billions of years, spreading intelligence and complexity throughout the universe. Or we might be near the end, one of many evolutionary experiments that flourish briefly before extinction. Or we might transform ourselves so profoundly that the question of faster than light travel becomes irrelevant, replaced by concerns and capabilities we cannot currently imagine. The future is open, shaped by choices we have not yet made, by discoveries we have not yet uncovered, by events we cannot yet predict. What we can do is continue the work. We can study the universe, learn its laws, test our theories, build our instruments, train the next generation. We can maintain the infrastructure of science, the universities and laboratories and observatories that make research possible. We can foster a culture of curiosity and rigor, where questions are valued, where evidence matters, where truth is pursued for its own sake. These are the foundations on which future achievements will be built, whether those achievements include faster than light travel or take forms we have not yet conceived. The night sky, ancient and unchanging from our perspective, is actually dynamic, full of motion and change that unfolds too slowly for us to perceive directly. Stars are born and die. Galaxies collide and merge, the universe expands, carrying distant galaxies ever farther away. Light from the early universe, stretched by billions of years of expansion, reaches us now as faint microwaves, the cosmic background radiation that fills all of space. This radiation is a relic of a time when the universe was hot and dense, a uniform glow that has cooled and diluted but never entirely faded. Studying this radiation has taught us about the universe's age, composition, and evolution. It has confirmed the Big Bang theory, revealed the existence of dark matter and dark energy, and constrained the values of cosmological parameters with impressive precision. It is a window into the earliest moments of cosmic history, a record written in light that has traveled for over 13 billion years to reach us. Every observation of this radiation is a journey back in time, a glimpse of the universe as it was when it was young. This ability to observe the past is both a gift and a limitation. It allows us to reconstruct cosmic history, to understand how structure formed, how galaxies evolved, how the universe came to be the way it is. But it also means we can never see the universe as it is now, only as it was. The present is inaccessible at a distance, hidden behind the light travel time that separates us from distant objects. Faster than light travel would change this, allowing us to observe the present state of distant regions, to see what is happening now rather than what happened long ago. This would be scientifically valuable, providing a different perspective on cosmic evolution and structure. But it would also raise new questions. If we could travel to a distant galaxy and observe it as it is now, what would that mean? The galaxy's know is not absolute but depends on the reference frame, on how we define simultaneity across vast distances. In relativity, simultaneity is relative. Different observers in different states of motion disagree about which events are happening at the same time. If we travel faster than light by warping spacetime, we might create our own notion of simultaneity, one that does not match any inertial observers. This could lead to conceptual challenges in understanding what we observe, in connecting our observations to theoretical predictions. These challenges are not insurmountable, but they highlight the deep connections between space, time, and observation. The universe is not a static stage on which events unfold, but a dynamic, interconnected structure where the act of observation is itself part of the physics. This insight, central to relativity and quantum mechanics, will be even more important if we achieve faster than light travel We will need to think carefully about reference frames, about causality, about what it means to measure and observe in regimes where our usual intuitions break down. The technical challenges of building a warp drive or creating a traversable wormhole are matched by these conceptual challenges. We need not just the technology but the understanding, the theoretical framework that tells us what to expect, how to interpret what we see, what is meaningful and what is artifact. This is why theoretical work is so important, why we cannot simply wait for experimental breakthroughs, but must continue to develop the mathematics, to explore the implications, to build the conceptual tools that will be needed when the technology becomes available. If and when humanity achieves faster than light travel, it will mark a transition, a threshold crossed from a civilization confined to its local region of space to one that can roam freely across the galaxy and beyond. This transition will bring opportunities and responsibilities. We will have the ability to explore, to discover, perhaps to encounter other life forms and civilizations. We will also have the power to affect those environments, to leave our mark, for better or worse. How we handle this power will define us as a species, will determine what kind of legacy we leave for future generations. The ethical frameworks we develop now, the values we cultivate, the wisdom we gain from our experiences on Earth, all of these will shape how we approach interstellar exploration. If we go forth with humility, respect, and a commitment to learning rather than exploiting, we can be a positive presence in the galaxy. If we go forth with arrogance, greed, or a desire to dominate, we risk causing harm and ultimately undermining our own prospects for survival and flourishing. The choice is ours, and it is one of the most important we will ever make. These considerations may seem premature, given that faster than light travel remains theoretical and may never be achieved. But it is never too early to think about the implications of our actions, to consider the kind of future we want to create. The decisions we make today about how we fund science, how we educate our children, how we treat each other and our planet will ripple forward in time, shaping the possibilities available to future generations. If we want those generations to have the option of exploring the stars, we must start now, building the knowledge and the infrastructure and the ethical foundation they will need. In the end, the question of faster than light travel is about more than physics or engineering. It is about who we are, what we value, what we hope to achieve. It is about our place in the universe, our relationship with the cosmos that gave us birth. It is about the stories we tell ourselves, the dreams we pursue, the legacy we leave behind. Whether we ever build a warp drive or open a wormhole, the journey to understand these possibilities is itself worthwhile, a testament to the human capacity for wonder, curiosity, and imagination. The universe is vast, ancient, and beautiful. Light carries its stories to us across unimaginable distances, photons that have traveled for billions of years to enter our eyes and our instruments. We are privileged to live in a time when we can decode these messages, when we can read the history written in starlight and cosmic radiation. We have learned so much, yet so much remains unknown. The frontier stretches out before us, infinite and inviting, full of mysteries waiting to be unraveled. Faster than light travel is one of those mysteries. It sits at the intersection of our deepest theories and our boldest dreams. It challenges us to think carefully, to work rigorously, to remain open to possibilities while grounded in evidence. It reminds us that the universe is stranger than we imagine, that the laws of physics permit phenomena far beyond our everyday experience. Whether we achieve it or not, the pursuit itself enriches us, expands our horizons, and connects us to the grand tradition of human inquiry that stretches back to the earliest astronomers who looked up at the night sky and wondered what they were seeing. So we continue, we observe, we calculate, we theorize, we test. We build better instruments, develop better theories, train better scientists. We ask questions and seek answers, knowing that each answer leads to new questions, that the process has no end. We are part of the universe exploring itself, matter contemplating its own nature, consciousness seeking to understand the fabric of reality. This is our purpose, our calling, our gift, and in pursuing it, we honor the universe that made us and the future generations who will carry the work forward toward destinations we can only imagine, through means we have yet to discover. The stars wait, patient and distant, their light a bridge across the void. Whether we cross that bridge slowly, at the stately pace light permits, or quickly, through some manipulation of space-time we have yet to master, the journey is what matters. The exploration, the discovery, the wonder. These are the things that make us human, that give meaning to our existence, that justify the improbable complexity that allows matter to become aware and seek understanding. And so we look up, we dream, we work, we hope. The universe is large, and we are small, but we are part of it, and that connection is enough. It is everything.